Swayam Prabha. Digital India. Educated India.
There are many topics we all want to introduce. We want you to be excited about. But I will go back to what I am quite comfortable studying myself for quite some time. And those are two or three areas of chemistry. One is the atomic domain, where the new discoveries in physics in the 1920s and continued to later in the 1970s and 80s have given us a very good picture of what a molecule looks like and what are the electronic structure details of an atom. Approximately 92 stable atoms. One or two of them are still not very stable. 92 elements. We are clear about the periodic table. From 93 onwards, many of the elements are found only in high energy nuclear reactor system and so on. But 92 is too many. The whole of the world today is functioning on two numbers, 0 and 1. Everything, all data, all computers, all science which are internet replicated, all your communications, all the businesses, they only need the two numbers 0 and 1 in 64 processors, 128 processors, 256 processors, or 1020, whatever number, 1024 processors. Okay? And chemistry offers 5. Organic chemistry offers 5. A, T, G, C, U. What are they? DNA and RNA, the base units, okay? The nucleic acids. And inorganic chemistry offers you 92. Okay? Now, therefore, it is left to our imagination to build a world which takes into advantage all these things. If 0 and 1 alone can create so much in the last 100 years, I would say about 70 years, since 1950 onwards, when the computers became reality, and one of the earliest computers was actually assembled by a very famous mathematician called John von Neumann, in a laboratory called the Princeton Advanced Study Institute. He called it as MANIAC. And then there were many other computers after the transistor was discovered and the very large integrated circuits became the phenomenon, and the chips started coming in, micro level chips. Gordon from the Intel, Gordon Moore, came up with a law that every 18 months, the boards will become smaller by half. More processors will be there in the same board, and the power of the board will also increase by a factor of 2 or something like that. We have reached, or we are reaching, the limit of the Moore's law. Another few years, we hope real quantum computers will start becoming reality. They are already there in some sense. Some processors are there. People can do quantum algorithms and tests and so on. But all of this is two numbers. The superposition of two numbers and two states. What's the fundamental to all of this? In physics, the two numbers are also seen in reality as what are called the intrinsic degrees of freedom of electrons, many nuclei, and many others in the name of what is called the spin. The analogy is one-to-one. What you do here, you can take the analogy directly and build systems based on what you learned in physics. Therefore, if you think about chemistry, is much more complicated than that with 5 labels. What is A? Adenine. What is T? Thymine. Guanine, cytosine, and uracil. Uracil is used for messages, carrying messages, and therefore it's part of the RNA. Uracil replaces what in a DNA? AU. AT becomes AU. Okay. Adenine, thymine, that's a hydrogen bonded system, by the way. And GC, guanine, and cytosine, that's also a hydrogen bonded system. And these are so weak bonds, less than a few kilocalories, but they are there in 50,000, 100,000, 300,000, and so on, like the airplane's wing, which will never vibrate because of the 100,000 screws which are there everywhere, small screws. If you sit on the window, you can see all these plane screws. Engineering marvel. Biological marvel is already with us. Okay, that's our body. And all of physics, all of biology, all of life that you have. Therefore, science as a whole should be interesting to us. The most complicated engineering marvel of this country, of this whole universe, is the human brain. Most complicated engineering marvel. Because despite 60 years of training and research and other things, artificial intelligence is not able to succeed a brain's power. Okay? So you don't need to look at all these engineering marvels. It's right in your brain. Okay? And what are the processes which run on the brain? Simple electrical impulses and chemical data. Therefore, you look at chemistry, physics, and other things as essentially microcosmic, small, micro-level phenomena which in a large scale become so cooperative that you are able to run engines, you are able to run the human body, you are able to run, dinosaurs lived, obviously, according to all the fossils and other things that we have. Therefore, you see that science and scientific phenomena go back to ultimately the smallest of the constituents of matter, namely the atoms. That is probably the reason why when Richard Feynman was asked the question, if the whole world comes into a cataclysm and at the end of this, everything is destroyed, but the person who destroyed gives you one option, you can give one message to the future. What would that be? What would that message be? Did anybody read that? That matter is made up of atoms. That was the most important hypothesis. That's the most important information. From that, we can build everything. That was the idea. So the idea of atomic theory, atomic structure, and the formation of chemical constituents, molecules, transformations, everything is related, and it's a whole science. And in this, mathematics is intrinsically, it's woven. It's not something that we can say, well, I don't understand mathematics. You have to, at some point of time, you have to understand the mathematics. And the question is why mathematics is so powerful is also something we don't know. Okay, but everything seems to work well, including the discovery of quantum mechanics and so on. So what I wanted to do is to start with something very elementary. The hydrogen atom is something all of you have studied in the 11th standard NCERT textbook. I recall it, the atomic structure is there in the 11th standard book, right? So you all studied hydrogen atom, and you were given pictures of, the atom flying with the wings called the orbitals. Atoms don't have orbitals. It's our construction of understanding what will happen when we look at them, what kind of picture we will get. If you do today take a very detailed, very, very fine picture of the atom, you are able to see a cloud, which look very similar to all our pictures. So in that sense, the atomic structure, the atoms, the properties of the hydrogen atom are fundamental to understanding the properties of all the other heavier, larger atoms. And also, fortunately for us, hydrogen atom is an exactly solvable mathematical problem in the absence of any external field, magnetic field or electric field. We understand that hydrogen atom has an electron, and there are things which you cannot, certain questions don't make sense, but you keep asking questions that the electron has energies, the electron has angular momentum, and then these angular momentum can have specific values if they are projected in a certain axis direction and so on. All these things have come out of the observation of the spectra, experimental spectra of the hydrogen atom, the emission spectrum of the hydrogen atom. And in that, there is also one area, one place where you see, when you put these atoms in a magnetic field, you see that the spectral lines become doublets. And therefore, there is an additional thing which has not been introduced by the founders, the first set of people who contributed to the structure of atom, namely what is called the spin. It's an angular momentum equivalent, except that there is no classical picture or a mental picture that we can associate with what a spin is. It's not something that is like this, no. That's a very, very classical view. In all of mechanics that we study, we understand, we introduce spin as a degree of freedom that the system has. The degrees of freedom introduced by the spin leads to many things that we understand later through interaction of the radiation with the nuclei and with the electrons. So, experimental observation for all these things is you shine light not visible, light, radio, electromagnetic field. And then you have multiple things. And spin is also observed. And it happens to be a fundamental property. I believe most of history says it is Uhlenbeck and Goudsmit. But I read today morning that there was another scientist who had predicted the whole thing some few months before. His name is not cited. You will look at the internet to find out the name of that scientist. But George Uhlenbeck and Goudsmit discovered the degree of freedom, which is very important in chemistry. And then the great Wolfgang Pauli came up with an explanation, came up with a theory of spins, and the spins have become fundamentally important in chemistry. Spins are as intrinsic freedom. To understand spins, I have read many books and I see that one has to learn quantum electrodynamics and go back to more fundamental details before getting an idea of what spin is due to. Without worrying about all these, chemists are very, very practical people. It may be something has a property, but what can we do with it? And chemists are much more open-minded about making money using all the discoveries and ideas, and biologists are even better. And of course, medical profession goes to the top of all of this. Okay? All discoveries should eventually lead to something that gives the world a benefit and the individuals who discover. So if you look at it, the chemists are obviously more interested in using the property as much as possible and discovering the chemical world much more effectively. The most famous part of the spin, which the chemists use, is in an experiment called the magnetic resonance. Today it's a day-to-day requirement to understand magnetic resonance. And depending on whether the spin is a nuclear spin or an electron spin, it is nuclear magnetic resonance or electron paramagnetic resonance, electron spin resonance. The differences are, there are substantial differences, but the techniques are common. And the resonance here is the interaction of the magnetic component of the electromagnetic radiation, the oscillating magnetic component of the electromagnetic radiation with the magnetic properties of the nuclei or the electrons. The interaction of the electric component, oscillating electric component of the electromagnetic radiation with the electrical oscillations which are there in the molecule, dipole moments, quadrupole moments, and electronic moments, all these things, that becomes optical spectroscopy. Usually these are things that one studies as we go along. But let us look at the spin as a whole. In a separate lecture, maybe tomorrow or later, I'll tell you the story of the spin, and that it is quantized to specific values was due to the experiment by two people, Otto Stern and another person called Gerlach, who was his associate. Stern and Gerlach came up with a beautiful experiment, and the outcome baffled them. Finally, they came up with a very fantastic explanation. And my colleague in the department here, former colleague, he's retired now, Professor Chandrakumar, had given a fantastic lecture on the Stern-Gerlach experiment. Okay? I'll search for the video and make it available for you to read, to listen to. He goes back to the history of how spin comes out as a quantum mechanical phenomenon, as a quantized quantity. Okay? And for chemists, more than all the finer details, what can we do with this quantized quantity? People were trying to use the idea of spin to study a spectroscopy, a resonance phenomenon. You know, what is a resonance? What's a resonance? How do you define? In general, when you say resonance, what do you mean? What is resonance? Okay, that's from the organic chemistry. We're talking about structural stereochemical resonances. Yeah, that's a different context. Here, in terms of electromagnetic radiation and these properties, what do we call as a resonance? Physically similar phenomena, and if they are in contact, and if they are brought together, if the phenomena are brought together, something like that. Okay, reasonably close. Anybody else? Okay, now you shine light and you see colors, right? What is happening? Why do you see colors and why sometimes you don't see colors? Two harmonic oscillators, sir is here. Two harmonic oscillators, put them in, and identical length and identical mass. Oscillate, start the oscillation of one harmonic oscillator. What happens after some time? Why does it happen? The energy flows between the two systems and it's conserved. The total energy remains the same, but the energy flows between one system and back. Okay? When you shine radiation, the energy of the radiation matches a certain change that happened that can be also measured. See, all molecules are supposed to have fundamentally they are supposed to have what are called quantized energies. They are not having any arbitrary energy. If we measure them, we will measure only specific energies. Now, if you want to change the system from one energy state to another energy state, there is a property which allows that change to happen. If that property syncs with the radiation, then the radiation can be absorbed due to that property, and the molecule can go up and come down. So the radiation resonates with the changes which are happening in the molecule. Electrical oscillations. For example, if the molecule rotates, if the molecule has a simple dipole moment is something all of you know. There's a charge separation, and there's a positive charge center and a negative charge center. They don't coincide. Therefore, there is a dipole. And this dipole moment is responsible. You can experimentally measure them. Now, if the dipole is rotating, it's an oscillating electric field. If there is another oscillating electric field which can be impressed upon it, and it has the same frequency as this, it's possible that the energy transfers between both of them. And when they are matching exactly, it is called resonance. If they are not matching exactly, it is called off resonance. Okay? One is called on resonance or resonance, the other is off resonance. Therefore, the same thing. Like what you said, vibrations. Yeah, that's also an important one. Molecules vibrate with a certain frequency. When they vibrate, the dipole, electric dipole changes because the atoms go away from their equilibrium position, they come back. And they do this faster than the molecules rotating. The vibrational motion in a molecule is much, much faster in general than the overall rotational motion of the molecule. And therefore, if that vibrational oscillation of the electric dipole matches with an electric field radiation which is available for it to interact, then the energy can be absorbed. Or if the molecule is in a very excited state, the vibrational motion can transfer the energy back to the radiation, like what lasers are due to. Okay? The energy can come up from the molecule itself, sync with the radiation that you shine. You get two radiations. But the point is, these are called resonances because they match. The changes in two of these, either magnetic phenomena or electric phenomena, match with each other. And therefore, energy gets absorbed, energy gets dissipated, and you can see changes in the molecule. Light, everything, emission, whatever you see, it's all happening because the body vibrates or the electrons move up and down, and the transfer of the electrons from one energy level to another energy level. These are all quantum mechanical phenomena. Okay? We don't have a classical picture for these things. So this is a general principle of, when we say spectroscopy, this is a general idea. The interaction of the radiation with matter, whatever that is. Okay? Now, the electric component gives you optical spectroscopy, the magnetic component gives you magnetic spectroscopy, resonance spectroscopy, and the spins, which are intrinsic degrees of freedom of the nuclei and the electron, contribute to this resonance phenomena because the spins do result in energy level creation. And when the energy levels are created, the spins obviously are in a position to absorb the energy or emit the energy, and therefore there is a resonance phenomenon which happens. But unlike a typical optical resonance spectroscopy, where you shine light and then the molecule absorbs it, to observe spin resonance, you must first create an energy level difference between the two or three, whatever number. The spins are intrinsic degrees of freedom, they are quantized, and therefore they have multiple energy levels. But they are degenerate, they are one and the same, unless you have an external stimulus. The external stimulus is an external magnetic field. Once you put a magnetic field and put the nucleus inside the magnetic field, the spins result in the interaction of the magnetic moment of the nucleus with the external field, and then energy level differences appear. So, a population difference, lower energy, higher energy population difference, is created by an external magnetic field. It's the fundamental requirement. You go to any magnetic resonance laboratory, there will be huge coils, magnetic fields. These are needed in order for the nuclei to have different magnetic energies. Now, they have different magnetic energies. Some of them have lower energy, some of them have higher energies. How many have lower, how many have higher? That all depends on statistics. That all depends on the interaction between the molecules, between the nuclear spins. But assuming that we have an equilibrium, everything, whatever change that is happening one way is happening in the other way also, so that there is no net change. When we have an equilibrium between these energy levels, you see that the number of nuclei in the higher energy level is always less than, even by one number, one nucleus, always less than the number in the lower energy until you saturate them by shining that radiation. Okay? So we have a population difference in the field, in the presence of a magnetic field. Until now I have not written any mathematics. We'll do that later. But try and understand to have a simple picture. Therefore, if there is an energy difference, now you can use another external radio frequency, another oscillating field, because now you have a difference. So if you have radiation which matches that gap, and if it shines on the nucleus can go from the lower energy to the excited energy. But to do that, you must first have these differences. Static magnetic field in the laboratory achieves that. So you need two magnetic fields, a static magnetic field and one to induce the resonance. For absorption, you need another changing magnetic field, which is a frequency, magnetic field frequency. And what does it interact with? It interacts with the magnetic dipole. And therefore, you see oscillations happen. And nuclei absorb energy, they give the energy back. All these things were postulated early on when quantum mechanics was known, that the spin is a fundamental property for the nuclei. It was already known to Pauli and others. But then later on, when the nuclear magnetic moments were discovered, when the neutron magnetic moments were discovered, then people started worrying about molecules having nuclei with magnetic moments. Therefore, we must be able to measure them. We must be able to see changes. So people started doing experiments. And none of these experiments initially gave the result of a resonance. None of them. 3 experiments were reported by a very famous Dutch physicist, all 3 of them on the failure to observe magnetic resonance. Okay, published. Very famous Dutch physicist called Gorter, C.J. Gorter. But then there were other physicists who were looking at those things and decided there must be something else, and so they studied the phenomena much more carefully. And then there was this famous physicist in Stanford University called Felix Bloch. And then another one in Harvard University called Edward Purcell. 2 people. They studied the system far more closely with their associates, and they were able to find a resonance phenomenon, measurement, absorption signal. The resonance signal absorption was a very interesting story, which I think Professor Chandrakumar also will tell you. If I have the time to call him, invite him, I would invite him to give a couple of lectures to you. He's one of the best known magnetic resonance spectroscopists in the world, and obviously among the best in the country, even though he's 70 plus. He is the right person to tell you. But Felix Bloch was successful, and the story of his discovery is even more amazing. He's trying to locate in the sense of, let me draw a simple picture. So you have 2 energy levels, E lower, E upper, magnetic energy levels. It's the simplest system, a system called a spin 1/2 system, in the presence of a magnetic field, H0, okay, which we call as the direction of the magnetic field as the Z direction. Okay. So now you have this difference between them. So you want to shine radiation on it. Typically, spectroscopy is right like that, and therefore the number in the lower level, number in the upper level, number upper is usually greater than the number lower, except for saturation population inversion, which is a very special state for lasers. Okay, in general, in thermal equilibrium, this is what you get. N lower. Oh, I'm sorry. Yeah, this is correct. Yeah, sorry. Yeah, I'm sorry about that. Yeah. Okay, N lower is much larger. Yeah. What is this number? Number of molecules. Suppose you have a sample. You take a small microliter of the sample. In a microliter, suppose 1 liter is 1 mole. Let's assume that the sample weight is such that 1 liter has 1 mole. In a microliter, how many numbers you have? 10 raised to 17 mole, right? 10 raised to 23 is the number for the Avogadro number of atoms or nuclei for 1 mole. 1 is to what? Let's assume HCl. Take HCl, hydrochloric acid. Number of hydrogens in each HCl is 1. So if you have something like 36 grams of hydrochloric acid dissolved in some solvent, 1 liter. So it's 1 mole of hydrochloric acid. Now you take a microliter of that. You'll get 10 raised to 17 hydrochloric acid molecules, 10 raised to 17 protons. Now, all the protons have energy in a magnetic field will be in either this energy or this energy. The number in the lower energy, statistically speaking, if you don't do anything, more molecules will settle down in the lower energy state after some time, and less will be in the higher energy state. Okay? But it's also interesting in its own way. If you don't have the magnetic field, the system has zero energy. Okay? That's a zero energy. Both states will be here. Lower and upper will not have any difference in energy. You put in a magnetic energy into the system. And then what you see is more number of nuclei are in the lower energy state and less in the higher energy state. It looks like you have lost some energy after putting in more energy into the system. Isn't true? Number in the lower energy is much more, and number in the higher energy is a little less. Therefore, what is the total energy of the system? It's less than this. But you have added some energy also. So where does the rest of the energy go? They are not equal. You can say that. Yeah. We'll start with that simple thing. Zero energy is equal. All of them. The moment you put in a magnetic field, some go down, some go up. Okay? This energy is given by a frequency, something called omega naught. Okay? It's a frequency. So let's assume that you have zero energy. Not half the molecules go up, but half the nuclei, but less than half go up. Therefore, all of them have higher energy, but more are in the lower. So suddenly something has happened. You put energy and it has disappeared. Felix Bloch and other people were very, very smart. They understood that immediately that there are molecules and nuclei in the system which do not have the spin. The spin, when I said nuclei have spins, no one asked me which nuclei have spins. Do all nuclei have spins? Degree of freedom. Not all of them. Nuclei which have even number of protons and even number of neutrons do not have the spin degree of freedom. Okay? No spin degrees. Freedom. Nuclei which have anything else have a spin quantum number. But fortunately for us, every nucleus has more than one isotope. Okay? So even if you have a nucleus, a stable nucleus like carbon-12 is 6 protons and 6 neutrons, carbon-12 also has a carbon-13 isotope which is stable. Carbon-13 isotope is relatively small percentage, 0.07% of natural abundance. It's a small number, therefore the carbon atomic weight is not 12 AMU. You have to find out what fraction is 12 nuclei, what fraction is 13 carbon nuclei. You have to weight their masses and then calculate the atomic mass of carbon nucleus. That's a very elementary addition that you do in calculating atomic masses. Okay? Here, what happens is every nucleus, oxygen 16. See, some of the most important nuclei do not have magnetic property. Carbon is most important for us. 70% of our body is water, the rest of it has a large amount of carbon. Okay? Fortunately, proton has a magnetic moment because it is only one proton, 0 neutron. You take deuterium, 1 proton and 1 neutron, that also has a quantum magnetic property. It's not odd, even, it's odd. Okay? Only even nuclei have been observed not to have ground state. This is all called, see, when you study nuclear phenomena, multiple things happen. What is the ground state of the nucleus? What's the excited state of the nucleus and so on. The ground state, which is very, very stable. Carbon-12 doesn't have a spin quantum number. Oxygen 16 doesn't have a spin quantum number. Helium 4 doesn't have a spin quantum number, and so on. Therefore, what happens to this is that when spins acquire energy and distribute themselves in various levels, the energy in excess that you submitted actually dissipates into the system, and the rest of the system In thermodynamics, the way you call system and surroundings, in this field, you call this as spins and lattices. The lattice absorbs the energy, and therefore the system magnetically cools down and establishes a population difference. Now you shine radiation on the population difference. You try to match the population difference by getting all these excess nuclei into upper energy state. So after some time you reach 50-50 saturation. After that you cannot see any resonance, you cannot see any signal. Okay? So this is the phenomenon. This was noted by Felix Bloch very beautifully when he used proton magnetic resonance. He studied proton, water molecule. And proton has the largest spin magnetic moment among all the nuclei. Okay. We'll see those units and dimensions later. Okay? What the magnetic moment is, what property called the gyromagnetic ratio, which is responsible. Other things we can see later. But let's see a picture and a story first, and then put what are called the details into that. Okay? So what Felix Bloch did, or his assistant did, was to set up a coil which generates this frequency, radiation frequency, fixed value. Okay? Some number, 20 megahertz, I don't know the exact number, but some number. So it generates radiation of the same frequency. To create the energy difference, you put the sample in a magnet between the magnetic poles, electromagnets, and turn the power on so that the electromagnets become magnetized, and the magnetic field increases slowly from 0 in a very short period of time. From 0, it reaches a value, stabilizes. And once it stabilizes, it is in that value, and that value corresponds to this energy difference. Okay? If you increase the magnetic field, the energy difference will become even more, because the magnetic energies are proportional to the field that you put in. So the magnetic field is on, the coil sends the electromagnetic field, nothing is seen. Okay? Several days, they tried different configurations. We didn't know what exactly was the electronics in 1946. Definitely there was no semiconductor, there was no transistor, this was all diodes. Okay? All the electronics was built on what people knew at that time. And the magnetic field was also not stable. But then on one day he said, just before closing the lab, Bloch said to Hansen, close the lab, we will go out. Okay. So Hansen shut off the machine. Magnetic field he turned off. But while he turned it off, he was careful enough to watch the oscilloscope where the signal is supposed to come. He was seeing only a flat line. Nothing, no absorption. Suddenly a blip came in for a short period, and then the blip died. Something like that. Otherwise, it was a flat line. Flat line means no absorption. Okay? Electric field is not getting into the system. So Hansen looked at it, and he was not happy. He said to Bloch, wait, I'll join you in a few minutes. Let the field settle down to 0. I mean, they know the time. By the time it will come down to nearly 0 value. He turned the magnet on again, electromagnet on again. And again, a blip appeared as the magnetic field was growing before it reached the top value, and then the blip disappeared. He said, this is very strange. Call Felix Bloch, his supervisor, his boss. See what is happening. So Bloch looked at it, and he said, repeat the experiment 3-4 times. So they spent a few more minutes turning off the magnetic field and turning on the magnetic field. And they started seeing the blip. Each time when it was turned on, the blip was there, turned off, it was there, but then it did not stay, disappeared. Then Felix Bloch said, I will go back and check my calculation whether the magnetic field that I calculated to get this difference, whether that was the right field or not. I'll go and check the field. So he went back, came back to the lab after the corrected calculations were done. He came up with the right number and then turned the magnetic field on and set the magnetic field at that value where the blip was happening. At that value he fixed, the blip stayed, did not go away for some time. And that was a discovery of resonance, magnetic resonance. And Felix Bloch reported this in a short paper with 3 authors. All 3 are very, very well cited. I mean, the others I know the name as Hansen, I don't know the first name, and then Packard. Okay. Paper appeared, and then later on they did many experiments, and they reported the nuclear induction signal. They call this as an induction signal because it is induced by the nuclei in the same coil through which the radiation was supplied. After the radiation is turned off, the same coil picks up the magnetic moments of the magnetic oscillations, and then that comes as a signal. Okay, the nuclear induction coil, and this was a nuclear induction experiment. And in parallel, Edward Purcell CEL, Torrey, and Pound, R.V. Pound, 3 people. So they published a very similar idea, the same sort of a resonance, and within months, 2 research papers appeared. They both came to the conclusion magnetic resonance was a real phenomenon that could be observed in the laboratory. 1952, they shared the Nobel Prize for physics. Okay, the first, I wouldn't say it's the first Nobel Prize for magnetic resonance. I.I. Rabi had been there. N.F. Ramsay was another physicist who discovered the magnetic moments. So magnetic properties had already been the study of many of really fundamental physicists. Ramsay was a very famous the analyst, and then molecular beam experiments, many things happened. But this was the first real experiment in magnetic systems, in solid systems, to observe a resonance phenomenon. First experiment. Well, if it remained like that, it would have been a physics experiment. Now, the nuclei have a magnetic field, a magnetic moment, and therefore they interact with the external field. The external field seen by the nuclei depends on what goes around the nucleus. Okay? The nuclei are not bare nuclei. Proton is not there. Hydrogen atom is not proton. Hydrogen atom is proton with 1 electron. Okay? The electron also has a spin property. Therefore, the electron also has its magnetic moment because it's an electric field, oscillating electric field. So there are local magnetic moments induced by the electrons. So if these 2 magnetic moments are there, the hydrogen nucleus may not see all of the external magnetic field, but it may be shielded by the electron's magnetic field. It's very simple, like you being shielded by your parents before us. And if your parents are very strong, they will not let you in here. If your parents don't care for you, or they say you go wherever you want, do whatever you want, you are the most de-shielded person. Nuclei are shielded by the electronic cloud for the external magnetic field. Now, if you look at it, different nucleus of the same nuclei in different chemical environment. If we think about very simple example of the famous experiment was ethanol, but let's take ethanol itself. CH3, CH2, OH. There are 3 hydrogens. CH3, there are 3 hydrogens. CH2, there are 2 hydrogens. There is OH, there is 1 hydrogen. Now, all of them are hydrogen, therefore all of them have spin 1/2, 1 spin quantum number. All of them have a split of energy levels in a magnetic field. What's the difference between them? The proton connected with the oxygen has all its electron cloud depleted because the oxygen is far more electronegative. Therefore, the electron density around the proton is much less. And proton can see the external magnetic field much more quickly. Suppose you put 100 Gauss. The proton will see 90 Gauss right away. Whereas, if you go to CH2OH, the hydrogen of CH2 has more electron density around the hydrogen because it's not directly connected to the electronegative nucleus. It's connected to carbon and then through carbon to the oxygen. Therefore, the proton density, electron density around the proton of CH2 is slightly more. And therefore, those electron magnets shield that proton more than the proton of the hydrogen. And therefore, you see that CH2 proton has a slightly chemically different environment compared to the OH proton, which is fully depleted, mostly depleted. And then you come to CH3. Pretty much all the electron density stays with hydrogen because, the electronegativity difference between carbon and hydrogen is so small. Carbon cannot pull all the electron density away. Therefore, you see 3 different types of hydrogen and therefore 3 different types of absorption frequencies for each one of them. So, a physics experiment has been turned into a chemistry monster. The moment you put ethanol into the system, the same NMR experiment now gives 3 signals. One signal for one proton, another signal for another proton, and a third signal for the third proton. Chemists have taken over the magnetic resonance. Okay, from that point onwards. How many molecules are there today? Approximately how many have been synthesized? Any idea? How many? Few million? Few tens of millions. About 38 or 40 millions. By the time I finish my sentence, probably another 2,000 molecules have been. So many labs are, yes. Yeah, that's a bare proton, yes. The shielding will be 0. That's called the bare proton signal. Yeah. If you have to see a H plus in a magnetic resonance system, you will see it at the lowest magnetic field for a given energy difference. Suppose this is the electromagnetic radiation frequency. The H plus has no electric field around it. Therefore, if you subject a H plus to a magnetic resonance, it will be seen with the magnetic field, the smallest magnetic field, because all the magnetic field will be seen by the proton. Yes, that's true. That happens. Which hydrogen? Okay, this is right away you can see that if you see the absorption frequency pattern, a spectrum looks like this generally, isn't it? That is, it has some intensity, okay, and then there is an absorption. Okay, this is frequency. Okay, this is a general nature of spectrum. This can be inverted for depending on the phase that you measure. But the point is, instead of frequency, now we have here the magnetic field, H naught. Okay, because you see, in the absence of the magnetic field, the nuclear energy levels are the same. But if you increase the magnetic field from 0 to H, energy levels increase like that. Okay? So this is the lower energy, this is the higher energy. It's proportional to the magnetic field. The mathematics we will see later. The mathematics of how this happens, etc. This is a conceptual introduction. Okay? So you can see that now what you have done is you have an experiment in which the coil has fixed the radiation frequency. So that's the same. Therefore, which proton will reach this difference faster? Hydrogen attached, because it sees most of the magnetic field right away. Therefore, this will be the hydrogen. Did I answer your question? Who asked the question? You asked the question. Yeah. So which should be this one? Which one? No, what should be this one?
So this one should be the CH3.
No. This will be the CH3. Well, if it is as simple as that, chemistry is still not interesting. Okay? You only get a structure, linear structure. What is more interesting is that there is further patterns to that. Depending on, no, yeah, we have seen all of them as something like this. We've seen all of them something like this, okay? And that one like this. But there are 3 protons next to 2 protons. And there is 1 proton, and next to it there are 2 protons. Now, if you say that the electron magnetic field can shield the nucleus, and this proton has a magnetic moment, this proton also has a magnetic moment. The magnetic moments can also interact through the electric cloud, the electronic cloud, which is called spin-spin interaction. One nuclear spin interacting with another nuclear spin. Now, if you take that into account, the spectrum is even more complex. It's not one line, one line, one line. The spectrum becomes multiplets. And the multiplets are so easy to understand using a very simple Pascal's triangle formula that is basically binomial expansion coefficients. So easy to understand. Now you see not only the chemical nature, but also which proton is interacting with which proton. Okay? Therefore, you see what is called near neighbor interactions. A protein molecule has all these individual proteins coil and then come together. So there may be a proton in one carbon which is probably 100 bonds away to another carbon, but the nucleus has folded, and so that proton is sitting right next to this proton. Okay? So it is spatial proximity. It is not a true bond proximity. Spatial proximity. You can see them. But to do that, you need to change the magnetic resonance experiment from one dimension experiment, that is one frequency experiment, to multiple frequency experiments called the 2-dimensional NMR, 3-dimensional NMR, and so on. And the more you bring in multiple dimensional frequency changes, you get to get all the details of protein structures. The primary structure of the protein through the sequencing, the secondary structure of the protein through the coiling, and the tertiary structure of the protein through the spatial coming together, overlapping. And therefore, you see, magnetic resonance then now has way off from the physics domain of an initial experiment. Doesn't mean that the physics has remained. The physicists have other interests using the same phenomena. In the whole of solids, magnetic solids, they study magnetic resonance phenomena in a very different way. But for chemists, this is a real problem of identifying molecular structure. A protein in a one specific configuration is the one which is most effective as a protein for its function. The moment you deconfigure them, you decoil them, the protein loses all its properties. And we call that as a denatured protein. You heat the protein. After some time, the protein loses all its coiling properties and becomes a flat line. All its chemical properties are gone. Therefore, biologically also you see that wherever hydrogen is there, which is pretty much all over the universe, okay, wherever hydrogen is there, you have a phenomenon. You can use a probe with one coil experiment or with parallel 2-dimensional models of NMR or even multi-dimensional. Yeah, all nuclei. We do multinuclear NMR, and I'm only giving hydrogen as a simple example because A, sensitivity for measurement is very high. You can get the signals very strong. B, proton has a very large, proton is widely there in all of the body. The water molecules all over the body constitute about 65% of the body's water. But the water molecules are in different cells. The protons are in different chemical environments. And the lattice surrounding the proton, one cell, the lattice is different from another cell. Therefore, you see that the protons in body They have so many different spin lattice properties, relaxation properties. They have so many different chemical shifts because of the environment. We worry about protons a lot. But carbon-13 nucleus is extremely important for all organic chemists. What do you mean boundaries?
Where is the highest point?
So the magnetic field determines what is the maximum energy separation. So if you apply a larger magnetic field, the energy difference will be more. The original spectrometer in 1952 or 54, the first NMR spectrometer, which was assembled by Varian Associates, I think this is the US company. They had a 20 megahertz NMR spectrometer. 20 megahertz referred to the radiation frequency generated by the oscillating coil, radio frequency field. And therefore the magnetic fields which were required were also very low. Okay. By the time 6 years later, the moment the chemistry was clear that you could see multiple signals, people immediately thought that if you want to detect hydrogens with very small differences in the electric field, and therefore very small differences in the absorption frequencies of the electron, of the nucleus, you must increase the separation between the energy levels, increase the magnetic field. Okay? So the 20 megahertz spectrometer later became 60 megahertz spectrometer, another one, which had a higher magnetic field that could go up to 60 megahertz for the energy difference. You know what we have today? 1000 megahertz experimentally. Probably more in some of the best laboratories. In India, I think there is 2 or 3 institutions have 900 megahertz spectrometer. Yeah, it's very expensive. The magnetic field that needs to support to get to that high level of, this is 900 megahertz frequency for the proton. And this proton 900 megahertz frequency will not be matching with the carbon resonance frequency. Carbon-13 resonance frequency. It will not be matching with the fluorine-19 spectrometry. It will not be the same as deuterium. Each nucleus has different gaps because that's a property called the gyromagnetic ratio. I will talk to you about that in the next lecture or next sometime. The gyromagnetic ratio is a nuclear property that physicists tell us. They measure and tell us. So if you're asking me what is the limit, today it is 1200 megahertz. Okay, that's the limit. See, the rotation or spin is just a name. It doesn't mean it is doing spinning, because that classical visualization of what is a spinning top that you used to play, those things don't come into the picture. We can't have a mental picture of this. So some time ago when I read an article in quantum mechanics, one said about visualization versus visualizability. Quantum mechanics is about visualizability. Classical mechanics is visualization. In addition to, you can model and you can basically picture every one of them with models. You can't do that in the nuclei. So you have to work with concepts and a whole new phenomenon, mathematical phenomenon. And you have to take this to the point that when you do an experiment, the conclusions of the experiment match with the predictions based on your theory. That's very important. So experiments and theory go hand in hand in all of physics, particularly in quantum mechanics, and so far we have not seen any exceptions based on what we have understood.